son 100% eléctricos. Es un problema.
Good morning.
Good morning.
Por último, de camping, ¿ya? Entonces, para hacer un huevo frito.
Good morning to everyone. It's a pleasure for me to introduce Dr. Alexander Arbierto, a Brazilian mathematician born in Peru. He holds a PhD in mathematics from the National Institute for Pure and Applied Mathematics in IMPA, and he completed a postdoctoral fellowship at the Federal University of Rio de Janeiro. He is currently a professor of this university. He was an affiliate member of the Brazilian Academy of Science and the Academy of Science of the Developing World. He was named a young scientist of our state, of the Rio de Janeiro state, in 2010 and also in 2013, and has held the title of Scientist of our state of Rio de Janeiro since 2020. His research areas are dynamical system, partial differential equations, and geometry. And thank you. And welcome, Alexander, and welcome to everyone to be in the second day of our conference.
Okay, thank you very much for the introduction. I want to thank the organizers, Jacqueline also, and for this invitation. It's a great honor for me to be here. And I will talk about a joint work with Obroha. He's now in the Czech Republic. And Diego, he was my former PhD student, and now he's doing a postdoc with Mahiko Fellowship in Poland. Okay. And well, I will talk about the flexibility of entropy. And first, the scenario I will deal with the geometries and flows on a compact manifold. So you take a vector field on your preferred compact manifold, solve the differential equation of this generated by this vector field, and take the flow generated by the solution. Okay. And so what is entropy? So entropy of a dynamical system will be a number which will measure the complexity of the dynamical system. Okay. So in particular, when this number is large, this indicates that the system is very chaotic. So, okay. So this is a number, it's an important number in the theory of dynamical systems. There are two types. So you can talk about the entropy of a measure, invariant measure. So this is a measure theoretical entropy. But you can also talk about the topological entropy, which measures the complexity of the system globally in the manifold. Okay, so the measure theoretical entropy was developed using the information theory studied by Shannon, and the other one was introduced by Adler, Komheim, and McKendry. Okay, so I will try to give the idea how to calculate the entropy. So the idea is the following. So you take your manifold and you fix on a scale epsilon and discretize the manifold. So each dot here you can think like a ball of radius epsilon. Okay. And what happened is that so in this blue arrow, so you can think like this ball goes to this ball like a translation, for instance. And then, so nothing happens in some sense, okay? However, if you have two arrows going out from one dot, so it means that there are points in this ball that are separating in the future by the action of the dynamical system. Okay, so this indicates that there exists some complexity inside of this ball, in some sense. And then what you do is, so you fix the scale, you fix a time n, and then you more or less count how many different errors go out from one point. Okay, so since this indicates that there is some chaos inside this ball, so you count them. Okay, actually you count you take the maximum cardinality of this. Okay, so you try to get the maximum complexity at this scale in this time, and then you calculate the exponential growth of these numbers. So like this. So this gives you asymptotically the complexity of the system at the scale epsilon. Okay, and then you take the scale goes to 0, so you're doing this calculation more refined way. Okay, and this is the definition of the topological entropy of the dynamical system F, and similar definitions holds for measures and flows. Okay, so this is how you calculate the topological entropy, and by definition, by construction, it's telling you how complex is the behavior of your dynamical system when the time evolves. Okay? And then there is this question by Katak. So he asked if the entropy can be calculated in a more or less monotonical way, in some sense. So you can achieve the topological entropy using subdynamics in a continuous fashion, something like this. Okay. Well, the answer is no. So there are systems with positive entropy which are minimal. So this says that there are no topological subdynamics on this system, and they are uniquely ergodic. So this says that you do not have many invariant measures. You only have one invariant measure. Okay, so in some sense the entropy jumps from 0 to the full topological entropy. So it is not in a monotonic way. Okay, but then he defined this property he called the intermediate entropy property for what he was thinking. So what he said. So we'll take any number between 0 and the topological entropy, and then he asked that there is some measure such that the measured theoretical entropy of this measure is exactly this number. So you say so you have a spectrum of from 0 to the topological entropy, and each point of this spectrum you find a measured theoretical subdynamics with this entropy. Okay, and he proved that. So like I said, this example is only continuous, but he proved that if you go to a higher regularity, so he proved that if you take a C2 diffeomorphism on a surface, then you have this property. So the measured theoretical entropy varies continuously in some sense. Okay, and he conjectured that this holds for any dimension. Okay, and well, this question there is a lot of research on this question. There are many partial results for geodesic flows, skew products, some partial hyperbolic deformations I will talk about later. Okay, so there are many results on this subject. Okay, but as I said, so this property is from the measured theoretical way. Okay, and then we propose some similar property, but in the topological fashion. So I said that the system has entropy flexibility if you take any number between 0 and the topological entropy, and then now you find a compact invariant set K such that the topological entropy of this on this subset is equal to this number. Okay. So now you want so you're asking that the topological entropy behaves in a monotonic way. Okay. And the first theorem, what we prove, is that for C1 generic diffeomorphisms, C1 generic means that there is a residual subset of diffeomorphisms such that any diffeom in this residual subset has the entropy flexibility, and also this is holds for flows, okay, for flows in three manifolds, okay. And I recall that the C1 generic diffeomorphisms are in some sense, is a larger class than C2 diffeomorphisms. Okay, and we also conjecture that this holds for the same for any dimension. Okay, so this is our result in the spirit of Catoc's theorem. However, you can say that okay, but if you are saying that many systems has this property. But what happens if I give you some system, so you can you check if there is this property or not? Okay. And what happens is that our methods are strong enough to deal with specifically systems. Okay. So we can deal with hyperbolic dynamics, sectional hyperbolic dynamics, multi-singular hyperbolic flows, and Rovella-like attractors. So, well, these are some classes in dynamical systems that we use a lot. But however, the most famous is this kind of sectional hyperbolic attractors, which the most famous example is the Lorentz attractor. So this is a picture of the structure of the Lorentz attractor. So it's an ODE. And what happens is that so the dynamics takes this rectangle and evolves like this. So this rectangle becomes this triangle, and then you put together here, and so the dynamics going around on this in this fashion, something like this. Okay, and well. It is an attractor which has a fractal transverse structure, and this is the draw of the attractor in different angles. Okay, but it's kind of famous by the butterfly effect or something like that. Okay, but our methods deals with specific dynamics, not only for generic dynamics. Okay. Okay, and so, like I said, so our methods also, so in some sense, let me just come back here to the main theorem. So like I said, so our result holds for diffeomorphisms and for vector fields, okay? But in general, for vector fields, it's more difficult to deal than for diffeomorphisms. I will explain why. Okay, and so in this sense, this theorem is more difficult for flows. Okay. However, for diffeomorphisms, specific diffeomorphisms, then it is more difficult if you allow partially hyperbolic dynamics. So partially hyperbolic dynamics is like a hyperbolic dynamics, but you have a stable, unstable bundles, but also a center bundle which you do not control very well. It could have zero Lyapunov exponents, and very, very crazy things can happen. However, our methods also behave well with some kind of projections, and then we can deal with partial hyperbolic dynamics with one-dimensional center bundle, such that the center foliation is a uniformly compact center foliation with trivial anonymity. Well, this is some technical assumptions. But for instance, if the center bundle is one-dimensional and the unstable bundle is one-dimensional also, then our theorem applies. Okay, so this is the main theorem, but many other dynamicists study some other kind of systems that, like this, so robustly non-hyperbolic, non-transitive diffeomorphisms, and this kind of system belongs to the class of we deal. So we can prove that in many other situations for partial hyperbolic dynamics we also have entropy flexibility. Okay. So these are the results, and I will talk a little bit about the methods. So, like you said, the results are for differentiable dynamical systems, right? But in reality, our methods are for we use topological methods. So we deal with topological dynamical systems. And actually what we do is to deal with, we start with the shift operator. So the shift operator is just, you take a sequence of zeros and ones, any sequence, and then you shift from one position, the sequence. It's a very famous and simple operator, but it encodes the most of the chaotic dynamics. So since the work of Ismail on the horseshoe, so he find that this shift operator describe very well the chaotic dynamics using this kind of the techniques of symbolic dynamics. Okay, but we not use the shift operator. We use a subclass of this, which we call subshifts of finite type. These are given by some matrix, so you do not use all of the sequence, just some allowed sequence. But perhaps the best way to see this subshift of finite types is like the following. So here you think you have 4 letters, 1, 2, 3, 4, and then you have a graph with some arrows. And what happens is that the sequence that you allow, you only allow a sequence that follows this arrow. So if you start with 1, then the next letter can only be in the sequence can only be 3, and then can only be 4. But now you can take a sequence with the next symbol is 2 or 1, and so on. Okay, and then you also shift this, and this gives us a subdynamics of the shift operator, and this is what we call a subshift of finite type. Okay, and I will not talk about more about the main thing of this subshift of finite type that I characterized by the shadowing property. So a subset is of the shift has the shadowing property, if and only if it is of this type. Okay. Well, but like I said, so we are not trying to do only with diffeomorphisms, but also for flows, and then we need some extra structure, which we call the suspension flow. So the suspension flow is a very general mechanism, a very general construction. So you take any homeomorphism F, and you take a rough function whole over there. Okay, and so you take the product of the manifold with R, and do this relationship, this equivalence relation, and then this gives you a flow. So okay, there is the definition, the formal definition, but it's easier to see in a picture. So here we have the space, the manifold X, okay, and I'm choosing the rough function to be constant equal to 1. So the height of this construction is 1. But it could be any function, okay? And what we do is, so you generate a flow, which is like this. So you take any point and you move upwards in a straight line, okay? And when in the top, when you reach the roof of the roof of the construction, then you teleport to the base, but you teleport to the point generated by the action of the diffeomorphism F. And then you're going upward, teleports, and this gives you a flow. Okay, so this is a general mechanism to construct from an homomorphism and a rough function a flow. Okay, the only thing is that, so this curve here, I'm choosing constant, but in general it's a continuous function, so it's a continuous graph. Okay, and okay, and so these are the main thing. So just let me come back to this statement. So if you say here, if you see here, so in some sense, in every of this list, there is some kind of hyperbolicity hidden inside this example. So they are not hyperbolic, okay, but they share some resemblance of hyperbolicity. And actually what we do is using other tools from differentiable dynamical systems and differential ergodic theory. So we use other tools to find horseshoes, which was introduced by Ismail, okay? However, these horseshoes are not exactly the horseshoes of which Ismail built, but what we find are horseshoes generated by this structure. Okay, so the horseshoes that we find are conjugated to subshift of finite type after a suspension. Okay, so this is why. So the method is one key thing of a result is to find these horseshoes inside on these examples. Each of these examples is treated differently, so we need to be careful to find those horseshoes, and moreover horseshoes that have large entropy. So recall that we are dealing with the entropy. So okay, and also in this theorem, okay, so it is another kind of construction. It's different from the other ones, since it's a generic construction, but we need to deal with the aid of the robustness of these horseshoes to deal with generic diffeomorphism. Oh, anyway, just I'm saying that what I'm saying is that one part of these results is to find those horseshoes. It means one part is to find subshifts of finite type, which have the shadowing property that are our main tool, and to find this suspension of these subshifts on inside of our dynamics. Okay. After when we find that, then so we will deal with the ergodic theory of such horseshoes, and in the case of diffeomorphism, we only deal with the entropy of measures of the subshift. However, when we deal with suspensions, so there is this Abramov formula which relates correlates the entropy of measures of the base with the entropy of the measures of the suspension flow. And the relation is given, is almost like the entropy, but you need to divide it by the integral of the rough function over the measure. Okay? And so, like I said, so for flows it's more difficult, this problem, because for flows, I need to control the numerator, which is given by the base, but I also need to control the denominator. Okay? And the problem is that this function rho, you don't know how this function is. So you need to control a general function that appears. So this really is a difficult step in our result. Okay. So the main technical result is the following. So you take any subshift of finite type. So this is a purely topological assumption statement. So you take any subshift of finite type, and you take any suspension. You can take any suspension. Okay, and then you take the suspension flow, and you take any number between 0 and the topological entropy. Okay? And then, well, we find a compact invariant subset such that the topological entropy is equal to C. And this is our goal. So this gives you the entropy flexibility of the dynamics. So I mean, I find some, okay, this is a measure, but I find some subset such that this entropy is equal to C. But to do this, I need to control all of the invariant measures inside the compact set and calculate this quotient for all of the invariant measures. And this is very difficult, but since if you have many invariant measures, and then this is more tricky and more difficult. Part of the result is that this subset is constructed in such a way that the dynamic is minimal, so you do not have any proper invariant compact subsets inside that. Okay, so the dynamics is very homogeneous in some sense, but also in the measure theoretical way. So it is uniquely ergodic, and this is the most difficult part, to show that there are only one invariant measure inside this compact subset. And this is very difficult, but it's great for us, because if you have only one invariant measure, then I need to deal with this quotient just to capture one measure. Okay, and what we do to control this, in particular in this statement, what we do is to construct, using the shadowing theory, we construct a nested sequence of compact invariant sets that they are becoming more and more minimal in some sense, and we are throwing a lot of invariant measures in this construction. So we construct a sequence of compact invariant sets such that in the limit, which is the intersection of them, okay, in the limit you get a minimal dynamics, and you only have one ergodic measure, and along the sequence we approximate these quotients by C plus 1 over n, something like that, and then when n goes to infinity, so we reach the entropy equal to C, which is required which is what we want. Okay? And a final remark is that, by definition, the intermediate entropy property, which I told you was defined by Katok, not implies and is not implied by the entropy flexibility. So in principle, they are separate, they are different notions. Okay? However, it seems that, and our methods are saying in some sense this, that the entropy flexibility is stronger, since once that you have there is only one invariant measure, then the entropy of this measure must be C. And so in particular we recover the intermediate entropy property, and then our result recovers all of the previous results on the intermediate entropy property. So this is really a generalization using topological methods. Okay? And well, then this is the story that I want to tell you. Thank you.
Any question? Any comment?
First, you don't need any mixing property in your lab result, okay? And
No.
have you imagined what is, just for the topological class theorem, have you imagined a large class, specified systems, I don't know, where
So-
this can be true?
Yeah. So okay. So we use the oh, sorry. We use the subshift because we deal with sequence and renewal sequences, and so that all of that machinery of the theory of shifts. But actually, what we only do, in some sense, is the shadowing property. Okay, so we think that this could be achieved only using the shadowing theory, perhaps with some extra hypothesis, but I think Oprova, there is some student of Oprova that is pursuing this. So, but so for us, so since we are using words and the theory of words and linking words, so it's more comfortable for us to do with subshifts, and it was enough. But I think that you only need the shadowing theory. Okay.
Any other question, comment? Thank you, Alexander, for this nice to introduce Dr. Lara Bossinger, a Mexican mathematician born in Germany, and a friend and colleague from the Institute of Mathematics at Unam, Oaxaca campus. I consider that Lara is one of the best young woman mathematicians researchers in Mexico. Her research expertise is in the toric degeneration, cluster variety theory, Newton-Okonkov theory, tropical geometry, and representation theory. As you know, she just received in August of 2024 one of the 4 UMALCA 2024 awards. This award is given to mathematicians under 40 years old who are permanently affiliated with institutions in Latin America and the Caribbean. In addition to her excellence as a mathematician, Lara is deeply committed to her institution, always seeking to collaborate and get involved in its activities, and to supporting and promoting the work of the Mexican Mathematical Society also. She is a great example of the well-rounded mathematician in many aspects, and I am truly glad that she is part of the Mexican mathematical community. Thank you, Lara. Welcome to this conference.
Thank you so much, Gabi. Thank you so much, Jacqueline, for this excellent organization of the workshop. I'm so happy to be here and to meet so many of you for the first time. It's being kind of in the Latin American math community and pushing that collaboration forward is really one of my passions. So thank you for having me. I want to talk about a project that I got involved with about 3 years ago, 2022. And this is a new rising collaboration between combinatorics and algebra, algebraic geometry on the math side, and particle physics on the side of physics, quantum mechanics, and in particular scattering amplitudes. So what I want to share with you today is this. So it's going to be quite a bit of physics in my talk. I'm not a physicist, I'm not an expert in physics, but I'm going to tell you where the physics or the math come from that I study, so I have a bit of motivation. And within physics, we're in quantum field theory. So in quantum field theory, just very basically, physics want to understand particle interactions. And as we're no longer, as we go to the quantum world, it's no longer possible to exactly predict what the outcome of such interactions are. So we're dealing with probabilities of interactions and probabilities of outcomes. And within physics, there are functions that determine the outcome, the probability of a certain outcome in these particle interactions, and they're called scattering amplitudes. So this is a function that is defined on some space, kinematic space, that models the particle interaction, and the outcome is this probability. And typically, these functions they're very complex. They're generalized polylogarithms. We can compute them as iterated integrals, but they're hard to understand. And what I want to tell you throughout this talk is essentially 3 points. First, the first two are more on the physics side. First is, what are these functions? The second is, where are they defined? Like, what are the spaces we're looking at? And then the third point is about cluster algebras, which is part of combinatorial algebra, and that's my field of expertise. So if you have any questions throughout the talk, feel free to let me know, feel free to interrupt me. I hope I can answer. So let's do part 1. What kind of functions are we dealing with? And the functions we're dealing with in the physics literature, they're called Goncharov polylogarithms. In the math literature, they're more often called generalized polylogarithms. And this is their definition. So we start with this iterated integral. This input a1 to an is usually called singularities of the function. Z is an argument, but we can think of it as a function depending on all of these n+1 variables. And this is how it is set up. So examples of these functions include logarithms, normal logarithms, exponentials of logarithms, and also more general logarithms. We have the LINs, and we have this function, for example, if you know about it, it's called the Nielsen polylogarithm. So we get a whole class of functions that we can express in this way. So these functions are hard to deal with. I mean, already the definition, really, I'm more like an algebraist, so if I see this definition, I get a bit scared. Like, calculus was never my favorite subject, and up to now in this project, fortunately, I was never in the position having to calculate one of these functions. So my physics friends, they're actually way better in calculus than any mathematicians I have collaborated with, so they take care of this.
So
but
the condition equal to 1, the first variable is what?
yeah, so if you don't have any singularities, this is constant 1. And then if you evaluate z to 0, we have this extra condition that it is 0. So these are like the starting values. If we don't have any arguments, and then here you can see how the function with n singularities depends on those with n at the previous n-1. Yeah, and then we have to integrate. Or we have to find friends that do. So it gets more interesting here on the next slide, because so these are complicated functions. For me it's hard to do calculus, but fortunately mathematicians got involved, and in particular Dur, Gangel Rhodes. Dur is a mathematician, and they studied a bit more like the structure behind the functions. Like, the idea is to take this function and see what is actually going on. Can we abstract some algebraic combinatorial data that will, guide us through the horrible process of actually dealing with these functions? And here's also where Goncharov really was important. So this recursive definition of the integral, the recursive integral, we also see that appearing when we start differentiating. So the differential of such a Goncharov polylogarithm is a sum depending on the polylogarithms with less singularities. And you can see that in every differential step, we get like a D-log form here that splits off a certain expression, rational functions in the singularities. And given this recursive differential structure, Goncharov defined the symbol map of a Goncharov polylogarithm, where essentially we just pick out this argument, right? So all we do from here to here is, this is again recursive, we take the symbol, and here we express the argument of the D-log in a tensor product. So this allows us to pass from this space of abstract, horrible, polylogarithmic general functions that I don't know how to compute, to a space where we just deal with tensor products. And there's a lot of structure hidden here. I've pointed out one or two properties, the distributivity, that allows us to play a bit with the arguments that show up here. And there's more that come from the shuffle product itself, from shuffle products on the Goncharov polylogarithms, and so on. So we see more algebraic structure rising. In particular, we can now associate to a Goncharov polylogarithm its symbol. And its symbol will be a tensor product. This tensor product consists of words, which would be the simple tensors. It's a sum of simple tensors. And the arguments that appear are called the letters. So we pass from the polylogarithm to its symbol, which is an alphabet of functions on these arguments. Great. So here's examples. Here's an example. The first example is the LIs itself. So we can compute the LIs also recursively. This is the expression as a Goncharov polylog. The first one is just a logarithm of 1 minus z minus the logarithm of 1 minus z. So if we start taking the symbol, well, this function just has symbol minus 1 minus z. We're already in a log. And then every time we go one step further in the index, where we get this argument picked out. Right, so this is the first and easiest symbol of a polylog. And with this example, we can already start computing more complicated Goncharov polylogs with two singularities. And this exercise, I think if you're already bored or tired and with a very dense schedule here, you can now take this function and just with this slide, verify that that's its symbol. Okay. Especially for students. It's a good exercise. You should do.
When is due?
Huh?
When is due?
It's due by the end of the talk. You have 20 minutes. We check in the coffee break. You can hand it. Okay, so this is great. Until here, I would expect if you're motivated, you can do it. The next slide is already a bit more involved, but I want to have this because it's the first example of actually a scattering amplitude. So if we go to a certain model, this is not a real world model, but what we're assuming here is we have 6 particles. They are light-like, massless, and we want to compute the scattering amplitude in this particular model that is called n equals 4 super Young-Mills. It's a very nice supersymmetric model, not modeling the real world, but physicists, theoretical physicists love it because we have so much symmetry to deal with. After we manipulate this function, we end up with an expression of this form. And I'm really cheating here because before symbol calculus, and before especially this 2010 paper where they have this result, computing this function was extremely complicated. Feynman was the first person that really kind of brought forward some methods on how to compute scattering amplitudes. And this function, as it would be defined by Feynman, is an infinite sum over integrals. So we have an infinite sum over certain graphs that have 6 leaves, and inside anything can happen. And what we're looking at here is the outcome of this function if we cap this infinite sum at 2 loops, maximally allowing 2 loops per graph. And then this paper was still very revolutionary because it gave us this very explicit and compact expression of this function that used to be an infinite sum of integrals. It's still not very nice to look at, and before I actually go into details and tell you about the symbol of this particular scattering amplitudes, I have to tell you a bit more about what is the space where it is defined, so that these functions vi here that appear, for example, make sense. because these are certain coordinates on the kinematic space. Any questions on Goncharov polylogarithms or symbols? Good. So the next step is a black box. And I admit this very openly because it still, to me, remains mostly a black box. But what we're going to do is we're going to step through this portal that Penrose opened in the 60s of taking space-time as it is. So this is Minkowski space-time, four-dimensional real vector space, Euclidean space, with a certain inner product. So four-dimensional as we have the three space dimensions and time. And we pass through to twistor space. So what Penrose revolutionized here was the idea of picking a certain isomorphism between this real Minkowski space and some complex space. And the complex space is called twistor space. And what happens as we step through this portal of Penrose is that many things change. For example, we have rays of light in Minkowski space, and they just turn into points in this projective space, complex projective space. And if we have massive particles, points, they turn into Riemann spheres. So there's many things happening in this process that I will not be able to explain. So we just take it as a black box, but the basic idea is of picking out a clever isomorphism between a real four-dimensional vector space passing to a complex projective space. And this has many effects on the side of the physics that we know on the left-hand side. So for example, there's some invariants, some symmetries that we observe in space-time that become very apparent and obvious on the projective side. This had revolutionizing effects in differential equations that physicists study in space-time that have now formulations in terms of complex and algebraic geometry and can be dealt with, for example, methods like sheaf theory. And in scattering amplitudes, the effect was like on the slide before, that we get new expressions that are really compact and manageable on the projective space, where they were really hard to compute on the Minkowski space. So, in our particular example, this is what we're going to do. And now this is due to Hodges in this 2013 published paper, where he suggested a particular way of how to pass from Minkowski space to complex projective space. So this is not just one map, this is a whole theory of different ways of transforming Minkowski space into a projective space. And this is the one that we're going to use, or that was used in this scattering amplitude case that I showed you before. So if we start with the particle configuration in this nice model, super Yang-Mills, n equals 4 super Yang-Mills, instead of having our particles be points or rays of light in Minkowski space, they will now turn into points in a projective space. So this particle configuration turns into n points in CP3. And with these n points in CP3 can be parameterized, and we're going to parameterize it by taking coordinates for choosing coordinates for each of the points and writing them in a matrix. And now the minors of this matrix parameterize our system in the sense that every point in our CP3 is represented by such a matrix, and these matrices have satisfied determinantal identities. In math we would call them Plücker relations. In physicists call them, I forgot the name. Never mind. Are there physicists here? So yeah. Anyway, so we have determinantal identities that now parameterize our system. Now we can parameterize our space with these symbols depending on four indices and the determinantal identities. And this is very closely related to my favorite space in algebraic geometry and in math, that is a Grassmannian. So points in a Grassmannian are exactly 4 by n matrices of full rank. And we're not exactly in this case because I started with points on projective space, but they're close enough. Great, so this is my outcome. If I go through twistor space portal, I end up with a space that is very much related to the Grassmannian, one of the nicest spaces in algebraic geometry. And now I can tell you the outcome of what's the symbol. So if I go back to this slide, you see here there are these VI's appearing in the expressions, XI's, and these are now coordinates on this, this Grossmannian space, on the twistor space. And this is my notation that I will need. So if I'm in the case where I only have 6 letters, or like when n is equal to 6, I don't actually need to remember which 4 points I chose. I can also just remember the 2 points that I didn't choose. So I have this nice compact notation. And now I can express these V and X's in terms of these minors of my matrix. And this is the expression. Like I don't expect you to really absorb this in one slide, but if you would stare for a bit longer and you have like a combinatorial mindset, you might notice some similarities in all of these expressions. And combinatorially, we have the following phenomenon. If you pick any such expression, like V1, this corresponds to a quadrilateral in a hexagon, where the numerator is determined by 2 parallel edges, and the denominator is determined by the 2 other parallel edges. And this is an observation that was made in this 2010 paper, and it is really interesting for me because these triangulations or quadrilaterals and n-gons are like one of the combinatorial structures that govern cluster algebras, this algebraic structure that I really like. So, are there any questions up until here? Okay. So let me tell you then a bit about cluster algebras. I will not give you the whole definition, but just to give you an idea of why I get really excited when I see triangulations of n-gons. And this is like my one slide summary of what a cluster algebra is. So with cluster algebras, we're now totally deep into pure math. We're in algebra. We're dealing with commutative algebras. And they are particular algebras that are defined recursively. They have certain important elements which are called the cluster variables. They generate our algebra. And we have a recursive way of going through this algebra by taking one set of clusters, a maximal algebraically independent subset, and moving to another one. And this process going from one to the other is called mutation. We have lots of combinatorics in this picture. Usually one cluster is determined by a quiver, an oriented graph. And the mutation is a local operation on the quiver that will tell me how to go from one to the other. So in one of the nicest examples, we can generate a cluster algebra from triangulations of an n-gon. And this is the example where we start with a hexagon, no, 5-gon. Pentagon. Gracias. Sí, a veces se me complica. Esta charla la doy mucho en español, como cuando cambia. Pero bueno, okay, so we start with the pentagon and the triangulation of the pentagon, and we associate these particular variables, cluster variables, to the diagonals. And then I have this formula that tells me, okay, from one pentagon, if I now want to switch the triangulation, I want to flip one of these diagonals. So that would mean I pick a quadrilateral and I change the diagonal to the opposite diagonal, like I did here. Then I associate a new variable and I associate according to this formula. Right, so in the case of a pentagon, there are 5 different triangulations I could choose. Think about the exterior parts being labeled so that these are not all the same. And then I get this collection of 5 different cluster variables associated with the diagonals. And the algebra I would define here is generated by all the variables I found along my sequence of mutation. And it is inside of a field of rational functions generated by the first 2. And this is pretty much the procedure. It changes, it gets more complicated, the combinatorics get more complicated. It doesn't always satisfy periodicity. Sometimes it just never stops. The mutation procedure never stops. I get infinitely many variables I would have to throw in here. But the general idea of what a cluster algebra is already visible in this example. And so this now tells me, in particular, oops, oh no, I did something. de lectura? No.
No,
La otra.
completa.
De la... Yeah, my Portuguese is pretty much non-existent, unfortunately. So, great. So, in particular, there is a cluster algebra associated to these combinatorics that I already observed that seem to be somewhat important for the symbols. And more generally, in this Grassmannian, for this Grassmannian, we always have a cluster algebra. Right? So, in all of these cases, in this nice model, there are cluster algebras, and the smallest example suggests that they might be relevant for determining the symbol alphabet. And this is essentially how they are related. So in this case of n equals 4 super young mills, scattering amplitudes for n particles, the case n lesser or equal to 7 is the one that I presented, where the cluster algebra here has a finite collection of these special variables, and all of them, or the set of all of these cluster variables determine the symbol alphabet. So these are specific coordinates on my kinematic space, and they are enough to reconstruct the symbol of the corresponding scattering amplitude. Now, it goes, the story continues when n gets bigger, 8 or bigger, but it gets more complex. Because also on the algebraic and combinatorial side, we no longer have this periodicity. Our system gets complex, we have an infinite list of cluster variables. But still, there is a subset of these cluster variables that determine some letters of the symbol alphabet. And there's also new challenges coming actually on the side of the symbol, where we have some letters that are no longer algebraic. They involve square roots. So we have to be a bit more creative, but even they can still be determined from this algebraic and combinatorial data of the cluster algebra. Now, there's a bit of criticism if we're working in this n equals 4 super young mills model. And that is because it is a toy model, it is far from reality, there is supersymmetry that does not apply in reality. So in physics, people would really like to be able to deal with the standard model that describes particle interactions in our real world. And then the natural question is, okay, these cluster algebras are really nice and cute for n equals 4 super young mills, but can they actually tell us something about the standard model or QCD? And actually, I'm not really sure how I'm doing on time because I don't know when I started. But I think I have more
Yeah,
time.
you have time.
Okay. Okay, so then for the last few minutes of my talk, I want to tell you where my work starts and what we can do beyond this toy model of super young mills. And before I can do that, I have to give you another way through this portal of twisted theory, and that is another way of how I can parameterize a configuration of light-like particles. And now there's like one important change here, and that is that I'm no longer working in this n equals 4 super young mills model where I had a lot of symmetry, like supersymmetry, conformal symmetry. But I leave these assumptions out, and I'm just taking any light-like particles, and they can now be any. We're now in this standard model of in the real world. And if I take these and I go through another twisted theory portal, the points in Minkowski space, the particles in Minkowski space, turn into n pairs of matrices. So we have two vectors, lambda 1, lambda 2, in C squared. And they form a 2 by 2 complex matrix. And the fact that we were light-like turns into this condition on the matrix. Normally here I would have the mass squared of the particles. And as I'm assuming it's light-like, we get that it's 0. But okay, so these are a few technical details. In the end, my configuration of n points in Minkowski space turns into a pair of two matrices, 2 by n. Both of them are of full rank, and they satisfy this condition that if I multiply one matrix with the transpose of the other, I get 0. In particular, we can define an algebraic variety that models these particle configurations of this form. It's called the spin helicity variety, these pairs are called the helicity spinors of the particles, as they encode the helicity. And these are now pairs in another space I really like of matrices in the Grassmannian 2, and that satisfies this condition. So we passed from a particle configuration in Minkowski space to a very nice algebraic variety that is defined inside a product of two Grassmannians. And as the Grassmannians have cluster algebras associated with them, it was also not too, maybe not too far to expect that also this new variety has a cluster algebra associated with it. And that's where I started working on this project with my collaborator Jan Romley. So, what can we say in this case? Well, here's the first example of working now within the standard model with just 5 particles. So, in this case, luckily, the hard computation of what is the scattering amplitude has been done. And there is a physicist, Johannes Henn, working in Munich, the Max Planck Institute for Physics. So his working group is really pushing hard on the analytic computations of symbol alphabets and scattering amplitudes. So thanks to his work and his collaborators, we have this list of 31 letters that determine the symbol of the scattering amplitude. And we can formulate it, again, in terms of these symbols, brackets, ij. They're minors on the 2 different Grassmannians. So the one in angle brackets would be a minor of the first 2-by-n matrix, the square bracket, a minor on the second 2-by-n matrix, a determinant of a submatrix. And these are the letters expressed. And what we found, my collaborators James Strom, Rosglu, and I, was that 30 out of these 31 letters are in fact products of cluster variables or permutation copies. So what was observed 2010 on this nice model Super Yang-Mills also holds if we go beyond that into the standard model. There is one interesting observation, that one letter did not appear in our list from cluster algebras. And it is interesting because on the physics side, this is the only letter where also physicists are not sure if it actually has physical meaning. So I told you that these scattering amplitudes are infinite sums of integrals, and when we cut this integral at a certain point, the phenomenon appears that we see spurious singularities. So these are singularities of the function. When we cut it at a certain point, that will disappear if we would continue summing the other integrals. And this W31 is exactly one of those examples. Okay, so now to finish a bit of an outlook, I gave you a bit of a taster of how cluster algebras are relevant in the computation of symbols, of scattering amplitudes. But they play a role beyond that. There is, so I focus now on the letters that appear in the symbol alphabet, but there's also rules of how these letters can form words, and these are called adjacencies. And in our work, we also discovered that these adjacencies of how we're allowed to form words can be predicted by cluster algebras to a certain degree. There is further work that just appeared on the archive this year about what happens in QCD when we go to 6 particles. So we're still not very far in number of particles, but the next step is already being worked on, and we have similar results. There are partial results, we don't have the full answer, also due to the complexity of the cluster algebras in this case. And there's like 2 working groups on that. So one is the working group of my colleague James Drummond in Southampton, and the other one is a working group in Providence, Brown University, where they did similar computations. And then the last part is something that I usually present as the motivation for this whole symbol calculus, and that is the idea of setting up a bootstrap for computing the amplitude once we know its alphabet. And that's really where we want to get with the whole cluster algebra application. We would like to get to the point where we can predict a symbol alphabet from the cluster algebra structure, and then physicists can set up a bootstrap and check that, oh, actually, in the space of polylogarithms on my kinematic space, there's only one function with this symbol. And this has been successful in cases where we already know the alphabet, and the hope is to get to the case where it will actually help us predict the functions beyond the possibility of the analytic computations. So that's all I would have to say on the math. I would like to use this opportunity to advertise a new book series that we're just setting up at ICMAM. So I joined ICMAM this year as an editor for this book series. And we are having, it's the first call of publishing work in algebra analysis and logic. It's about, I think, just one more month that our call is open, so a bit tight, but in case you have some paper lying around that falls in this area, it can be also a research article, it can be an overview paper, it can also be a good master thesis or bachelor thesis of students that might not get into an international journal. So we're accepting all kinds of works of visualizing more work in Latin America in these areas. Thank you very much.
Thank you, Lara, for this nice talk. Any question, comment, any other question? Yeah.
I just have a short question of the last slide, where you said that somebody predicts adjacencies. Can that be related maybe to graphs?
Yes, so I mean there's a lot of graph theory in scattering amplitudes, and I only kind of mentioned this on the side. So there's the so-called Feynman graphs,
Yes.
that are the ones that index this infinite sum of integrals. And yeah, so there's a lot of work in that direction. I am not familiar of any paper where the adjacency would be read off from the graph.
Okay.
But yeah, there is certainly a lot of graph theory and lots of combinatory problems in that direction of Feynman integrals as well. Yes, thank you.
I have a comment or a question or whatever. This family of pentagons or whatever are also calling graph theory as the associahedro, right?
Yes.
It's the and in the next step or whatever, you take the hexagon or this is the idea. Okay. And obviously you can do exactly the same with other polygons, right? Or not really?
So these two combinatorial observations, they coincide in this case. Unfortunately, if we go actually to the spaces that are relevant and the cluster structures that are relevant for the physics, we have the hexagons and like the n-gon interpretation in these cases where n is less or equal to 7. So that's unfortunately just n is 5 is pretty simple still. It's only n equals 6 and n equals 7 where we have combinatory coincidence. Unfortunately, once we go to 8 particles or more, the combinatorial structures here don't have the periodicity anymore, and we don't have the interpretation of this is, I don't know, triangulation of a certain polygon or polytope or So we have this nice coincidence in the small cases, but the research that has been done so far suggests that they diverge after this point.
Okay, thank you, Lara. Any other question, comment? Well, thank you, Neil, for your talk. We'll come back at 10:30.